Let's go. Lesson 78, sound waves. We will describe how a sound wave moves. Now, this is the basics that I wanted to try and get through today, is just to talk about, we keep talking about sound. When you hear a sound from a musical instrument or from my voice or from a speaker coming out of your computer, what is the mechanism that the sound is getting to you? Like why can you hear the sound? Well, what happens if you were underwater? Would you be able to hear the sound? What happens if you're in space? Would you be able to hear the sound? These are some of the basic questions I would like to get to the answer to. So to do that, we need to understand firstly, what is sound? And then secondly, what is a sound wave? And then thirdly, if we want to understand what a sound wave is, how does it move? And they're going to be the basic sort of things. I think I would like to finish this PowerPoint up today with just finishing up on what the speed of sound is, and then not necessarily the speed of sound in as how to calculate it, but what it is in different materials. Sound waves form the start of our next topic, which is sound. Now it says here topic 13. The reason it says topic 13 is because technically this is the 13th unit that we've done so far. You may be like, no, it's not, but you've got to count it in a weird way, because ultimately, even though motion was 3 units and electricity was 3 units, three topics. This is area technically for in VCE terms. This is unit 2, area of study 2. So that's what this is. This is option 210, how the music's making instruments. I'm not going to go through this slide here. This is just a slide that I ripped straight off the internet. And this is more for my benefit than it is for your benefit, because what it means is that it lets me know, okay, I have, according to the Victorian government, I have to teach you guys this stuff. But if we have a quick look here, on completion of this unit, students should be able to apply wave model to describe and analyze production of sound in a musical instrument, and explain why particular music combinations of sounds are more pleasing to the ear than others. So that's going to be interesting to sort of talk about. We need to discuss what cadences and chord progressions are. And if you've got a history of music, then you actually have a bit of an advantage. I don't. So if you're sitting there thinking, oh, Sir's going to be like, we'll explain things. I don't. So I'm going to be learning this at the same time. But it's going to be interesting. I think, like, intuitively, I know that there is such a thing as called a C chord, and it's very nice to hear, but I don't know what a C chord actually means. So that's going to be something that we're going to have to figure out. I'd actually like to get some people from the music department to come in and speak to us during a couple of lessons, just to sort of go through some of the ideas in a practical sense, because that's the other reason why I like this topic, is it's pretty practical. This topic can be broken down into 3 main ideas: modeling sound, sound production, and sound detection. Modeling sound is going to be the first thing we're going to do. By pretty much the end of Tuesday, but by the end of Thursday, by the end of the week, I expect all of this to be done. By the end of tomorrow, I expect to at least be done here. Thursday is this, and then probably Friday is going to be this guy here. But I reckon that's going to be a pretty interesting and difficult concept to teach, but we'll get to it. Sound production, explain resonance. That's still related to this idea of reflection. Investigate human voice box. Investigating a variety of musical instruments, the similarities and differences in sound production between types. That's going to be interesting. And then sound detection. Like, how do we pick it up? What is timbre? This is the one that I'm most nervous about, because I have no idea how to teach you guys that. But yeah, let's talk about let's start with the first and probably most important concept. Again, I'm going to keep looking at my watch to make sure I don't go over time. what is sound? I think that's a pretty good place to start. I guess we are going to be exploring this in many ways, but we're going to start with what is sound? And this is a bit more of a scientific definition, but still. Sound is a vibration that moves as an acoustic longitudinal wave. Now, we're going to have to explain what longitudinal wave means, but yeah, like acoustic means that you can hear it. So yeah, we have to explain what that word means, but at the moment, that's what sound is. It does this through a transmission medium, such as a gas, a liquid, or a solid. Now, a transition medium means a transition medium is anything that something passes through. So this is all waves, all waves except for light need some kind of transmission medium. You need to move. Waves can only move if they're moving through something. You try to think about like a water wave. Imagine a water wave without water. You couldn't have a water wave without water. You couldn't have a sound wave without air. You need to have something to move through. So what is sound in that way? So sound is a way energy can move from one place to another. And this is these are sort of 5 separate sort of ideas. Sound is, we've already firstly said it's a vibration that moves away. But sound is a way that energy can move. If you think about this, right? If you play a loud enough sound carries energy with it. It's a way of radiating energy. So when we talk about, and the reason I bring up energy is because energy is kind of like the thing that's been tying everything together this year with physics, because we always talk about energy. And so when we talk about sound, we still need to talk about energy. Some sound can have really high amounts of energy. You can actually, I'm sure some of you guys may know, but there is a shrimp in the bottom of the ocean called the mantis shrimp. And the mantis shrimp is able to make a sound so loud that it actually is able to blow apart other sea creatures. It does this by flicking its legs out so quickly that it causes a pressure wave, which is still technically sound because sound wave is just vibrations in air, so it's still a pressure wave. And it does that so quickly that pressure wave just blows apart small sea creatures. Mantis shrimp, look it up, it's kind of cool. But yeah, it's able to produce this sound, and it's able to produce. The reason it's able to produce it is because it's making large amounts of energy. Now, how does sound move then? I'm realizing this slide is not very good because there's way too many ideas on this one slide, but that's okay. How does sound move? Sound moves when one particle pushes on another particle. So if you look, this particle will push onto this particle, bump into this particle, and so on. And that's how sound is able to move from one place to another. So we've got 4 ideas here. And these ideas are very different. And as I said, I apologize. I probably should have spread these ideas out over more than one slide and group them a bit better. So let's try and understand them. Sound is a wave. That's the first thing. Yeah. The second thing is all waves need to move through something except for light. But yeah, whatever. So it needs to move through something. The something is going to be a medium. Sound equals waves. Waves need medium. Done. Sound is a way energy can transfer from one place to another. Wave equals energy transfer. And if you guys remember when we talked about heat transfer, we talked about radiation and stuff like that. And the fourth one is sound can move. How does it move? It's a particle. It's moving as particles. Sound equals particles pushing. We actually discussed this. If you remember, like we spent a lot of time talking about the particle model. Well, this is the particle model. It's just a bunch of one particle pushes in another particle. You can explain sound as just particles pushing another particle. And of course, if you've got a low air pressure area, particles are going to move towards low pressure because they're going to be pushed away from high pressure. So that's what, yeah. Now, here's some questions that I've got for you, just generally questions. Like first things first, and I'm going to ask this to the chat. Can you hear sound in space? Yes or no? And if yes, if no, because no is a weird answer, why not? Thank you, Morrison. Yes, no, why not? Why can't you hear sound in space? It's a vacuum in space, which means that there are no particles. Okay. One of the classic sayings is, I think it was like the tagline for Aliens, in space no one can hear you scream. It's because you can't scream. There's no air to push against you. There is no medium. What about underwater? Can you hear sound underwater? What do you guys think? Yes or no? Yeah, you can hear sound underwater. One of the ones that, if you ever dive into water, you can hear the click sound of the filter going on. You can sort of make like, I used to do a lot of, it's technically, yeah, this is how I grew up. I did a lot of, like, not like experiments. I don't want you to think that I went outside of the lab coat, but when I was swimming around in the water with my friends, I'd go underwater and I would click my fingers. I listen and I'd be like, oh, isn't it interesting? You can still hear that clicking sound underwater. Because obviously you can't talk underwater really because you get a mouthful of water, but you can still make clicking, and you can't clap because there's too much water in the way. I mean, you can still click and you can still hear that clicking sound underwater. And that's because, yeah, water is a medium. And even though it's not the same as air, but it's still a medium, so you can still hear sound through it. You can still create a pressure wave. So yeah, really good, guys. So now we have a way we can discuss what sound is. Sound is just a pressure wave that moves through air, moves through a medium. And it's a way that energy can get transferred around. As I need to rewrite this slide, I think, a little bit, but it does the job. So let's talk a little bit about this idea of, let's talk a little bit about this idea here. I started off by talking about longitudinal waves. Now, I want to discuss, and this is going to be the last probably 5 minutes I'm going to be able to get through, but I want to at least discuss, well, let's talk about these waves. What are these longitudinal waves? What is a longitudinal wave? So a longitudinal wave is this. There are two ways that waves can transfer. The first is called a transverse wave, and the second is called a longitudinal wave. Now, a transverse waves are ones where the vibration is perpendicular to the direction of the wave. What that means is, let's look at this transverse wave here. Okay, this transverse wave is going to the right. We can see that it moves to the right. And even though it moves to the right, you know, let me just draw a picture here. Even though this transverse wave, so let me just try this. Even though this transverse wave is moving to the right, it bounces its bouncing or its vibration is up and down. Does that make sense? Oh, whoops. Let me fix that. Its vibration is up and down. And if you were to take this angle and if you were to take this angle and the movement, the direction of the wave, you would see that that is a right angle. They are perpendicular. Some common examples of transverse waves include water waves. So if you think about the water, the waves move towards the beach, but the waves, even though they're moving towards the beach, you know, the waves are moving up and down. Another one is, of course, and I know that's classic from sports matches, the Mexican wave. You think about the Mexican wave. For those of you that don't know, the Mexican wave is where a crowd of people stand up, and then other people are sitting down, and then they will stand up when the wave gets to them. And then after the wave's gone past, they will sit down. Now the wave, you can actually see the direction that the waves go. The wave will actually go to the right or wherever. But how it does that is by people standing up and sitting down. So that's a right angle to the direction of the wave. Longitudinal waves are different. Longitudinal waves are ones where the vibration is parallel to the direction of the wave. So let's grab a look at this example down the bottom here. In this longitudinal wave, we can see that the compression, there is an area of high compression, and then straight after that, there is an area of before that, there's an area of low compression. And you might think, well, this doesn't really look like a wave. It's still a wave, right? It's still this, it doesn't necessarily look the same, but it's still a wave because you've got this area of, movement that moves. If you were to look at this picture above it, you could still draw an arrow, say this is the way the wave is moving. But the way, let me just draw the same color line, so it's blue. That's the way that the line is moving, but the vibrations are actually happening like parallel. So you can see here that the wave is getting squashed, whereas here the wave is getting before it's getting extended out. So that's how a longitudinal wave, and that's how sound is made. Sound is actually a pressure wave that comes out as a longitudinal wave. Now, it's hard to sort of think about this, but I sometimes think about it's really easy to look at when you see special effects with people. When you see someone that makes someone makes a loud sound, what they're going to do is they're going to, let's just say they yell, they're going to make a sound that goes away from them as some kind of pressure wave. And that's going to reach out to everyone and stuff like that. I'm sure if you guys have seen enough anime, then you guys would be pretty familiar with the idea of, someone, pressure waves coming away from someone. They don't vibrate up and down. They actually vibrate in and out as they come out of that person and so on and so forth. And if someone yells, and that's exactly how a pressure wave works. Yeah, so what have I got here? Have I got 5 minutes? No, I've got no time. We'll just leave it there then in that case. So because the next part is to talk about the particle theory, which I've just already touched on already, and then to talk about why this is going to be the question I would like you maybe to ponder now. See if you can come up with an answer before next week, because next week I'm going to ask you, why do you think that, and it's going to be based off this understanding here, but it's going to be, the question is going to be, why do you think that if sound travels faster through steel than through air. And that's going to be the main thing. So today all we talked about were these main ideas. Sound is a wave. A wave is a vibration of something that moves in a direction. We talked about sound as a way that energy can transfer, so it's a transfer of energy. But of course, we also finished up with sound moves by one particle pushing against another particle. Then we talked about what longitudinal waves are, and next week we're going to talk about, well, what do we mean by one particle pushing against another particle? Ladies and gents, that's it for today's lesson.